Okay, thanks for the introduction, and I would like to thank the committee to invite me to talk here. Today, I would like to present some of my recent ideas about Hodge theory. So the title is a Nonlinear Hodge Theory in Positive Characteristic. So the Nonlinear Hodge Theory is a term I formulated in a way which I think is suitable for my talk. So let me start with some classical. So let's talk about something about Hodge theory. So Hodge theory is a mathematical counterpart of the theory of electromagnetic force in physics. So this is a math part of the part of our nature. So let's look at the smooth projective variety. So if at all complex points, so you have a complex manifold, compact complex, and you have since it's projective, you admits calorimetric. It's non-unique, but you can take one. And the central theory of the Hodge theory is the existence of a unique theorem of harmonic forms. That means you give any class, diagram class, you will find a unique and smooth representative alpha, such that they in the same class and satisfy additional. This doesn't work. Okay. Anyway, so satisfy this Laplacian equation, and it has some consequence. Let's mention two. So first one is the so-called E1 degeneration of the Hodge to de Lang spectral sequence. So so you see, so the point doesn't work. So you see that you have the. Can you help me to make this point work? Anyway. So okay. Okay, so so you on the right hand side you will have the purely algebraic defined cohomology. This is a Hodge cohomology, or so it's purely algebraic defined. It's using the Charles topology. On the right hand side, you can also use in the Charles topology. You use the algebraic diagonal complex and take half cohomology of it. So you have so-called algebraic diagonal cohomology. And this purely algebraic defined spectral sequence is degenerate E1. So this is a very deep consequence of this theory of harmonic forms. And the second one is called vanishing. So for any ample divisor D on the space X, you will have this vanishing of the higher cohomology of this Young system, the dx plus d. And this have, this is have abundant application in algebraic geometry. So let's move on the non-abelian Hodge theory. Likewise, this non-abelian Hodge theory is also have a physical meaning. I mean, this is, you can say, this is a mathematical counterpart of the theory of the weak and strong force in physics. And its mass object, I mean, usually one setup is like this. You start with a integrable connection. So here take lambda equal to 1. So you will have a usual connection. And when you take the lambda equal to 0, you will get so-called Higgs bundle. So this is, you can formulate in one package, so-called lambda connection. So you imagine from moving lambda from 1 to 0. So when lambda is non equal 0, you get the nabla divided by lambda is actually just a connection. But lambda equals 0 is something objects which is different. And you have also so-called slope stability. So you fix I've already fixed some polarization Kerr metric in my context. So you have omega. So you can define this the degree respect to omega, and when there's this stable for any saturated proper connection invariant coherent subsheaf, you have this strict inequality. When this semi-equality is called semi-stable. And the central part, I mean, the input from the analysis is the existence theorem of the Hermitian metric or harmonic metric from the flat bundle to the given the connection you are asking for canonical metric, which is the so-called equivalent harmonic maps. So, but from the Higgs side, you will use Hermitian metric. So you have a collection of the works of Collier, Donaldson, Hitchin, Simpson, Wollenbeck, Yao. I mean, I only talk about the compact case. So that's the major player in proving this existence. So so that there's a state that for any stable flat bundle, respectively Higgs bundle, I mean, then you exist unique up to scaling metric H satisfy this this equation. So this is a nonlinear PDE, and this F perp is the trace-free part of the curved tensor attached to the twin connection of this Hermitian metric H. Okay. Where's lambda? Lambda is disappear because I take the perp. So if you take trace-free part. Where's lambda? So the lambda appears above. Here have a lambda. But oh, this one, I'm sorry. This is a adjoint operator of this Lefschetz operator. So you take the endomorphism valued forms, and then you take wedge product. Respect this omega, you get degree 2 higher endomorphism valued forms. And then you have the metric in our setting, because you have a background metric, you have a metric on the bundle. So you have this the L2 metric. So then you take a joint. That's it. Okay. Sorry, yeah, that's London. Okay, so then the one beautiful things out of this deep analysis is so-called non-abelian Hodge correspondence or non-abelian Hodge theorem. So this is really combination of the Lima-Hilbert plus Close-Simpson. But one special, very important case is Donaldson-Wollenbeck-Yao in the case of unitary connection. So this states that you have equivalence categories between the category of the complex linear representation of the topology fundamental group of your manifold and the category of the semi-stable Higgs bundle of your space with rational vanishing chain classes. And the second consequence is an inequality about CH0, CH1, CH2 on your bundle. So it's about discriminant of your Higgs bundle coupled with this your polarization is also non-negative. And then also you can say when it's you can say it's projected flat when it's equality achieved. And the third one is the so-called Kodaira-Saito vanishing. So for any, so this generalized Kodaira vanishing in the sense here consider more general coefficients. So the coefficient now is a semi-stable Higgs bundle, etc. with vanishing Chern classes. The original Kodaira vanishing is the case where E theta is the trivial one. E is the trivial bundle, theta is 0. And this statement, this vanishing, exactly reduced to the Kodaira Kn vanishing theorem. Okay. So this is a brief on this. So this series, I mean, really have many applications in algebraic geometry. And one point I want to point is that we also it's important to consider pairs. For example, in the Hodge theory, you can consider pair, you will get the mixed Hodge theory. And also the allowing singularity is also extremely important. Okay. So let's move to the positive characteristic work. So the first fundamental theorem is this Hodge theory in positive characteristics is a theorem decomposition theorem by Nonlinear. So it states like that. So K is algebraic closed, and this positive characteristic P, and X is smooth, and is W2K liftable. So the liftability means here, if you take, I mean, it's like you have a deformation along the P. So the W2K have a maximized generator P, and modality is K. So it's a thickening, right? It's a deformation. And also you have the assumption on the dimension is small. So and this in the character P you have always this geometric Frobenius, this relative Frobenius, it's a morphisms over K. So and the statement is that if you push forward this Diam complex via Frobenius, then you get something. You get some complex which is a OXP linear. And actually, it's decomposed. I mean, in the Dirac category, it's really decomposed into Dirac sum of this is a single complex. It's omega I shifted by minus I. So without this lifting condition, you have isomorphisms on this common sheaf of this of the push forward. This is a Cartier theorem. But when you have the liftability, then they show that this actually the complex decompose. And this, I mean, the consequence, I mean, I think for algebraic geometry, I mean, the significance is that this really gives us a purely algebraic proof. I mean, by spread out technique here I wrote here, it provides a purely algebraic proof of ion degeneration called a vanishing character 0. So yeah, in the statement you don't have you don't assume X is to be proper. I mean, it's smooth, but yeah, but turns out is using standard technique you can show this ion degeneration statement in character 0. So this is really for algebraic geometry. This is really a triumph of mathematics. I mean, we can prove some statement, which is we look at this, look at back this statement. I mean, so this is purely algebraic. I mean, as I said, this is everything is defined using Taylor topology, and the first proof is in a natural way. But now we can prove it using Taylor topology only. But you need more P. So okay, and I would like to remark that the condition here in the theorem of Nonlinear is almost optimal. So you cannot drop the condition, the smoothness, for example. Actually, there's an open problem by Illuzi. He asked that if assume x over k is only log smooth and replace the Delaunay complex by log Delaunay complex, and if whether this log Delaunay decomposition theorem hold, but we show that this actually does not hold. And you cannot, the liftability, I mean, when it's non-liftable, I mean, this classic example, count example by Renault, he constructs some algebraic surface where, in character P, where the Kodaira vanishing fails. So this is imply that the liftability is crucial here. And the recent work of Petrov showed that if you show that the dimension is p plus 1, then this is Ivan integration also fails. So this basically, this is really optimal as we can expect. So now we move to the nonlinear Hodge theory in positive characteristic. So I mean, so far, I mean, the theory really flows very smoothly. I mean, you have the I see that you have the analytic theory, and then you will see you have a KXP theory. Okay, but this is really the nonlinear Hodge theory in positive is relatively recent work. So so we start with the this August-Rogowski correspondence. So you have the same assumption. You have, as I did in Illuzi, you have a smooth space X, and you have you assume the liftability. Then there's an equivalence category between the category of the flat bundles with nilpotent curvature, P curvature, and the category of the Higgs bundle with the p-nilpotent Higgs field. So the P curvature of the connection is a unique invariant in the KXP for connection KXP. When this you have an integrable connection KXP, then you can define. You have a well-defined P curvature, which you're not able to see in KX0, because this in the case of KXP, you have the tangent. The tangent space, you have additional structure, so-called this the P structure. It's restricted algebra. So this is the P curve just measures the difference of your of this Frobenius P in the base and the Frobenius P on the fiber, so to speak. Yeah. So and this is actually very crucial. I mean, this invariant, the P curvature, to establish this correspondence in KXP. And but without P curvature, I mean P curvature vanishing, this correspondence is a theorem which is very classical. This so-called Cartier descent. So this is a category of the flat bundle with vanishing P curvature with the category of Higgs bundle with zero Higgs field. It's just a category of the vector bundles. This is, you can formulate this like to solving the flat sections of a connection KXP. Usually you don't have the full rank solution. But then this the Cartier said that the obstruction is the P curvature. When the P curvature is 0, then you have a full rank solution. And our first work in this field is we reinterpret the OV correspondence in terms of a so-called exponential twisting of the Cartier correspondence. The original approach of the August-Rogowski is using he explored the Azumaya property of these sheaf of PD differential operators. Here we show that without PD structure, I mean just assume stronger nilpotent condition, then this is really the kind of a twisting version of this Cartier correspondence. And you may also interpret this with PD version. You can also using this exponential twisting. But we didn't write down. But it just means that this you can do something very concrete differential calculus in KXP to produce very non-trivial correspondence. Now I want to move on the theory of His-on flow. Before that, I would like to say that the theory of His-on flow is a positive characteristic and of the Yang-Mills theory in physics. We do have a theory mixed characteristic, but here, since I'm only talking about the character P theory, so it's a positive characteristic. So it's not about the equation. So it's not about to give a character P differential equation. It's really about the analog in the output and the feeding. I mean, to like in solving this Yang-Mills equation, you use the hit method. I mean, you flow it. I mean, this here you have some discrete flow, and the output is important. I mean, as we will show. I mean, in the application. So let me first explain the core. First, the core definition of the His-on flow theory. So a His-on flow is a diagram. So the diagram is have two layers. So the bottom layer and the top layer. And the bottom layer is every term is a Higgs bundles, and the top one is a flat bundles. And from the upside, so from the inverse Cartier here, C inverse is a Cartier transform of OV in the OV correspondence to send the Higgs bundle to a flat bundle. And the downside is from the flat bundle to a Higgs bundle. So this is achieved by after choosing a suitable filtration. We call Hodge filtration here. So and then you will get another Higgs bundle, and keep doing this process. So at the first sight, this is really a soft definition. I mean, you can it looks like you can do arbitrary thing, but actually it's not. I mean, it's not the case if you put same stability. I mean, there's a lot of rigidness in this notion. So so I would like to divide the whole theory into two parts. The first part is more arithmetic. I call it the periodic flow. So we call a flow, a His-on flow is to be periodic if there's some positive integer f, such that this EF theta f is isomorphic to the initial Higgs field, E0 theta 0. So if f equal to 1, this is just one periodic. Okay? And the theorem is if you assume x is proper and is W liftable, for example, in the case of a curve, of any curve in character P over perfect field, or any here K is algebraic. Here is actually we assume K is a perfect. So you can liftable to WK, and you choose some such lifting. Okay, then there's equivalence of category between the category of the crystalline FPF representation of the pi 1. Here the pi 1 is the Ital fundamental group of the generic fiber of your lifted scheme. And we here also assumption on the small Hodge theta weight and the category of the periodic His-on flows with period f and level less than p minus 2. So here in a very special case of the theory is a case where Hodge theta weight is 0. And in this case, we strengthen our original theorem in this theorem. So here's the work with Jilong Tong. We show that this corresponds actually literally generalize classical correspondence by cuts about this unit F crystals. So in the cut theorem, I mean, they are basically it's local. I mean, you need to assume the existence of Frobenius lifting. But here we may simply remove it. And also we remove, I mean, the liftability of X2W. I mean, And then the second part is the more geometric. I call it a theory of a semi-stable flow. So suppose now X is projective. We call this flow is a semi-stable if every Higgs term in the flow is a slope semi-stable. Then here you will see this the theorem as kind of existence theorem of a previous mentioned existence of Hermitian Mills in XP. So suppose you have the rank of the bundle is small. So E0 is our initial Higgs bundle. Okay, you fix some Higgs bundle, and the assumption is the rank is small. Then there's a semi-state flow with the initial Higgs term. That means you can start with a semi-stable Higgs bundle with a small rank. Then you can keep flowing it, and such that every Higgs term is a slope semi-stable. And this flow is essentially unique. And also the assumption on the rank is crucial. That means if you have so as I mentioned earlier in the theorem of the Delisle, you have the dimension is small, and otherwise you have the counterexample and by Petrov on the Yuan degeneration. Here we have a similar phenomenon here. So here the recent work, my joint work with my student Bowen Liu. We show that actually when for any rank which is big, that means it's strict positive, strictly greater than P. So it's P plus 1. The first example is P equal 2 and the rank is 3. So then you will get an example which is semi-stable but not leading any semi-stable flow. So yeah, so this is this is not known before, but we actually we conjecture that every semi-stable Higgs bundle is leading a semi-stable flow, is so-called strong semi-stable. But actually, we showed that here. First, we proved that the small rank is okay, but now we know that this works basically only for small rank. For the semi-stable one, essentially yes. I mean, if you require every term is semi-stable. If you don't require this, certainly you have a lot of choice. For example, you can you can always take the trivial filtration. So let me show you that here. Here the freedom of the flow is, you see, the inverse Cartier is fixed. If you fix the lifting, the inverse Cartier is fixed. So the V0 nabla 0 is fixed, but the choice comes from the choice of the filtration field 0. So for example, you can take the trivial one, field 0 to be trivial filtration. Then you can also do that. If you don't, if you want to put any additional assumption, then you will get the E1 theta 1 will become V0, 0, and you can continue doing that. And you can always do that, but you won't get interesting theory always. For some example, such things interesting, but yeah. But as you asked about uniqueness, I said if you require E1 theta 1 to be again semi-stable, then this is essentially unique. So it's determined by the E1 theta 1. Yes. And actually, there's many other interesting phenomena happens in the flow, actually. Yeah. Okay, then let's talk about some applications. So here I list 5 applications so far, but actually there's more other applications. But our first work is actually so our initial goal is really to establish a character P or torsion P analog of the Hitchin-Simpson correspondence about the non-abelian Hodge correspondence. So then as an application of that, we can reinterpret the S. Mochizuki's Piatti-Uteshima theory using this framework. And the second is a breakthrough done by Greshnik on about the Simpson's motivicity conjecture on the rigid connections. So Simpson's rigid connection is that if for any rigid connection in over complex number complex numbers must be motivic. Being motivic means that it's coming from geometry. So coming from family of your base, a family of a variety of a base, and they're taking But here, this is a fantastic conjecture, but still open. But they made the breakthroughs on this conjecture, showing that for rigid connect, for any arithmetic model for rigid connection, you have some Frobennius structure. So this predicted by the motivic conjecture, because if you have family, certainly you have this Frobennius structure by taking the crystalline cohomology of it. But they can show that using in our theory. And Andre Lange also using the same theory of same-state flows to give an algebraic proof of the Bogomolov T-set inequality. So remember that we, in our above, here, so in this, this is Bogomolov inequality, which is this is pure algebraic statement, and its first proof is using Yang-Mills metric. Now you can prove it without Hermitian metric. Instead, you're using the same stable flow. Okay. And the fourth application I would like to mention is the algebraic proof, the Kodaira-Vannish theorem by Don Arapura. So he just observed that using the same stable flow, you can reduce this Kodaira-Saito vanishing by Sayre vanishing. So So this is also a very nice application. And the recent work with my joint work with Wang Jianping, we give also an algebraic proof of the so-called tensor product theorem for semi-stable lambda connections. So the classical one is like given two semi-stable Higgs bundles in character 0. Then we make a tensor product and take the torsion-free part, and this again semi-stable. Then the early proof is also by Yang-Mills metric, because if you take Yang-Mills metric and take a tensor product of it, it is against Yang-Mills metric, and then you will get this this tensor product theorem. Okay, so far any questions? Okay, if no, let's move on. Now I'm report some new things. I call nonlinear Hodge theory. So K is a perfect field. Now here I give a notion which is for any field. I mean, you calc 0 either calc P or calc 0. So K is a perfect field, and S over K is a smooth K variety. And we consider a smooth morphisms of it. So in our early case, the objects like we always consider a geometric bundle over S. Of course, for geometric bundles, it's smooth, but now we consider arbitrary smooth morphisms, so X over S. And now I define an integrable connection on F is to be a morphisms from the product of your tangent bundle to the total tangent bundle, and which splits this canonic projection from the Tx to Ts. So this is really give you a splitting of your the first exact sequence in the relating to 3 tangent bundles, right? So so give the image of your connections give you a foliation, the so-called transversal foliation, which So you imagine that you just lift your vector field on the bottom of S to the ambient space, right? So this is the geometric the image of this vector connection. And integrability amounts to the vanishing of your curvature. Okay. So if you like, you can call this a nonlinear flat bundle, because here X is you can imagine as a flat bundle over S. I mean, and this is the differentiable way is like that. So and a Higgs field on F is a morphisms. Now the target is instead of the total tangent bundle, here is a relative tangent bundle, and it's called Higgs field. You said another integrability condition is so the pseudo curvature. This is vanish. So in this for this pair, we call it this Higgs bundle of S. And I said if you can to distinguish from to make a distinction from the vector bundle case, then we call it nonlinear. And we have ample examples of such. Wait, move. Oh, it's frozen. Why? Oh, it's moved. Wait. Yeah, I think it's this. Yeah. Here now, then we can make a category by defining the arrow between the objects. You have a natural arrow, so make a category. And here I write the NMIC means the nonlinear integrable connections. I mean and subject to some condition question mark. And correspondingly, you have the NHIG, which is a category of nonlinear Higgs bundle subject to question mark. So the first set of examples certainly is coming from the linear objects, the usual Higgs bundle and the flat bundle as we talked above. And this gives you the linear one. And then this comes from, I mean, we know the connections can over one-dimensional, over curve, in particular over P1 punctured Riemann surface is really equivalent to saying that we are considering linear ODE. And now we can consider more nonlinear ODE. I mean, but the term is rational function. And you, for any such thing, you can only associate a nonlinear flat connection on the open part of your fine space to an open part of your P1. The second example of nonlinear objects is coming from the non-abelian Hodge moduli space. So you have, say, you have a family of smooth project variety. Now we consider the relative de Lang functor, and it's represented by this smooth morphism of S. And more than that, it's not just it's a smooth morphism. You also have the equipped with a canonic flat metric, so-called the Gauss-Meilling metric. And And when k equal to c, I mean in the field of complex numbers, you have this Gaussian connection have a purely topological interpretation through via this so-called isomorphism deformation. I mean so because topologically, I mean the X over S is really a fiber bundle. So you can identify any two closed fibers topologically, right? And in particular, their pi 1 can be identified. So if you have a representation of pi 1 of the one fiber, and through this identification, you will get a representation of the nearby fiber, right? And in that way, this we call, I mean, then, but this is well defined up to homotopy. Then this is really give you a well-defined so-called isomorphism deformation of local systems on the modern space. And this identification gives the topological meaning of the Gaussian connection. I mean, which purely algebraic defined by Carlos Simpson. In character P, we may put new conditions on new potency of P curvatures to obtain a variant of this consideration. And now we have also the counterpart in the Higgs side. So on the Higgs side, you have the relative double moduli space, which is parameterized the stable Higgs bundle, with version 10 classes, and using the universal objects, we can define some tautological non-abelian Higgs field, which is I mean to define it, it's a little bit involved using the Grothendieck special sequence. You can to map some maps from the up corner to the bottom. Anyway, so we can define explicitly some maps which make this G, the G, yeah, sign G, a nonlinear Higgs bundle. Okay. So a recent result by my student Fu Yishan and myself is the following properties about this non-abelian Higgs field. So first, we show that taking grading of the non-abelian Gaussian connection with respect non-abelian Hodge filtration, you will get this non-abelian Coulomb-Spencer. And the pseudo curvature of this Coulomb-Spencer is 0. That means this. So I mean, in the case when the base S is a curve, I mean this condition is vacuous, so always integrable. Then the second statement that no matter when the base is, you always have the integrability. So that after this, we get a Higgs bundle, nonlinear Higgs bundle defined as above. And the third property is about the gradiness property. So you have the GM action on the fiberwise GM action on the G, and then the third part says that the Coulomb-Spencer is compatible with this structure. And actually, this structure is very rich, and we are still exploring the meaning of this graded nonlinear Higgs bundle. And it's many new things occur in the nonlinear setting. I mean, yeah, and this is related to many classical things like Hessian morphisms, BB stratification, and so on. Sorry. Okay. So yeah. Now we move on the correspondence. So first, I generalize the Cartier descent to a so-called nonlinear Cartier descent. That means here the zero, you see, I said here the zero means that we consider a nonlinear flat bundle with vanishing P curvature. Okay, we can, we'll define the notion of the P curvature. Then if you the category of the nonlinear flat bundle with vanishing P curvature is equivalent to the category of the smooth S varieties. It's any, this is very, you have a smooth morphism over S. This we regard it as a nonlinear Higgs bundle with zero Higgs field. Then interestingly, this categories actually corresponds to some object which is a pair, which is not a smooth morphisms over your base and equipped with a canonical connection. Some connections are defined as above with vanishing P curvature. So this is kind of for me is symmetrical. I mean, in character zero, if you have a smooth morphisms, you basically you can do nothing about it. But now in character P, you can map this to another object, which is a different morphism, smooth morphisms, together with some additional data. So so this is the content of this nonlinear Cartier descent. And this certainly is compatible with the classical Cartier descent. And the second one is so-called the local nonlinear Hodge correspondence. So we assume now the base is liftable and the Frobenius also liftable. And then we have equivalence category for more objects. So here so-called the nu refers to new potency on the P curvatures. So so now you don't request this require this the P curvature to be zero, is to be nilpotent. Then you still have make a equivalent category, and this generalize the local Oxford correspondence for linear objects. Now here again, I mean you have morphisms, you have the smooth morphisms, you have nilpotent Higgs fields, then you obtain another smooth morphisms with connections, but a P curvature is a nilpotent. Now, and then the last step is to glue this local correspondence together by make an assumption. First of all, we assume we consider, I mean, the X over S, this is the projective. And the automorphism group, the relative automorphism group, is a principal G bundle. So here I only consider the kinetic component of this relative automorphism. So relative automorphism, I mean, you can imagine as a fiberwise automorphism. Okay? And this usually is just a group scheme, but it's not necessarily smooth. But here I assume it is smooth. So, and the G is a split reductive group. And I assume its Cox number is small compared to P. Then here we will get a global nonlinear Hodge correspondence in the sense that we assume only the scheme is liftable instead of putting additional assumption on the liftability of Frobenius. Then we will get an equivalence of category. Here we need to assume the P curvature is P nilpotent. Previously is nilpotent, but not necessarily P nilpotent. It can be P square nilpotent. So, but actually the proof extends more general situation. I mean, here you see I assume my smooth morphism is projective. But in the case of vector bundle, I mean, certainly it is not projective, it's affine. But actually the proof also allows us actually to prove that as long as the image of your P curvature or Higgs field is contained in the algebra bundle of a principal G bundle. I mean, it's contained some, because in the affine case, I mean, or more general non-compact case, the automorphism group is huge. So here we we assume the Higgs fields contain some finite dimensional thing, then the proof exactly works. I mean, the proof is exactly the same. Now, here is I want to say some application. So here, let me recall the theorem of August-Rogowski. They proved the following one periodicity, but the formulation is different from it. But I reform it in a way like that, and this also in a way is proved by Fardins. So you have a smooth probomorphisms of K, which is liftable to W2, and the relative dimension is less than equal to P minus 1. And let the H delam to be the relative diagonal bundle of degree D. Okay, and in this case, the Hodge sequence, relative Hodge sequence is degenerate at E1. And this relative diagonal bundle is equipped with a Gaussian connection and Hodge filtration. And then there's a natural isomorphism, or canonical and natural isomorphisms of the flat bundles of S. Here the meaning of it is that you can reconstruct this flat bundle, this relative diagonal bundle, using graded Higgs bundle. Okay, so here you take the grading. I mean, the left hand side reads. So you take the flat bundle, you take grading respect the Hodge filtration. Remember, this function appears in our flow, right? So here just means that in the flow you start with some flat bundle and you flow down to some Higgs bundle and you move upwards to some Higgs bundle using this inverse Cartier. Now it says that this is one periodic. That means your resulting flat bundle isomorphic to original one. That's the meaning of this the theorem. Then we can cook up with a non-abelian analog of this. So, but here I can only do for the local setting because there's some assumption about this image of the Higgs field, like mentioned before. I mean, if you the image, so you see the Dirac modular space or Higgs modular space. This is not proper over your base. Here we only consider this smooth locus. So this parameterized irreducible connection on the M side, or the stable bundles on the Higgs side. So this is non-compact. So that means that this automorphic relative automorphic group is a priori is infinite dimensional. Then in that sense, we can only do this local analog. So here we assume this the S and this Frobenius is liftable. Then we show there's a one periodicity. So in particular, I mean this is in a very. So look, the inverse Cartier is the inverse Cartier we defined above. I mean in the correspondence. So this gives a perfect analog of this non-abelian analog of this one periodic theorem of August-Rogowski and the Fardins. So I think still have 4 minutes. I can say one more recent result about construction of representation of pi1. This is really some expect theorem in work in progress. So suppose S is a proper of closure of the finite field, and we assume the scheme is lifted to W with a ring, and then we start with a smooth probomorphisms with the assumption that the relative automorphism is principal G bundle. Then here I really make a very condensed definition. I mean the so-called nonlinear fountain module. But here, just only roughly speaking, nonlinear fountain module is on F. Actually, it's a quadruple, but now I just on F means you have a connection. This is a connection on F, as I defined above, and you have a Hodge filtration, but Hodge filtration on F. Okay, it's satisfying the Griff transversality, and the hand phi is a forbidden structure. It satisfies a parallel condition. But if you, this is only very roughly speaking. But you can make it very precise. Actually, this structure here, this means that this moduli space of this Nonlinear Hodge moduli space is a nonlinear fountain module. Then the result is that if you assume G is liftable to a smooth group scheme over ZP, so that the G is a more P reduction of some smooth group scheme over this ring of periodic integers, and we assume the P is a large respect to the Cox number, then there's a functor from the category of nonlinear fountain modules of S with P nilpotent Higgs field to the category of the representation from the Ital fundamental group of a genetic fiber to your GFP. And this functor generalizes those constructed by, classically by Lin, Katz, Fontaine, Lafayette, and Fartins. And I want to mention that the proof is really relies on an ongoing project with Sheng Hao and Wang Jianping on a series of the canal flows for principal bundles. So, okay, I think I stop here. Okay, thank you.
All right, thanks for the talk. Any questions?
Are there any applications correspondence in positive characteristic? Do you get some interesting application in characteristic zero?
Very good questions. I think so far my theories is still to look at some phenomenon. About this. About the Gaussian non-abelian Gaussian connections. Some works in Daniel Little's work, and some other people's work in a more geometric way. So I don't have a very precise application. New applications. Maybe in some sense to produce representations. It's a different way. For me, even the notion you imagine that even you have some scheme which is smooth over W, projective, and if you can put, you can take the funnel, right? If you can put some forbidden structure as I define here, then you can produce a gamma representation into the automorphism group of your funnel manifold. For me, this is a kind of potential application, which is, the way to construct gamma representation is different from the classical one, because in the classical terms, you usually take a variety and take for example, the curves and take the periodic homology, and you have but certainly in that case, you automatically have the forbidden structure. Then you can make a representation on the gamma representation on the theta modules. But now here you have something more nonlinear. So if you would say this is something new, maybe it's new. It's different. I don't know if can get some new representation which can unconstructible. It's from the classical approach, which I don't know. And another thing is I think it will be interesting if you can define some nonlinear stability. Maybe in that case, you will have some more geometric application of this notion. But since you mentioned the character zero thing, I think the natural question is that if there's a character zero theory exists, a nonlinear Hodge theory of the field of the complex numbers exists or not. This is a very natural question, and I can tell you that such a theory also probably exists. But to establish, the correspondence, as we've seen before, it's really a challenge of some nonlinear Hermitian-Mills equation, which still in progress. And yeah, so I think, yeah, that's.
Thank you.
Okay. Any other questions? Okay. If there's no question, then let's thank our speaker again.